In March 2026, on a small coastal test plot in eastern China, a young engineer bent over a black panel tilted toward the sun. The wind coming off the sea was sharp, but the metal face was warm, almost hot, and along one edge, a line of white salt had begun to crawl outward like frost growing across a window. Clear water was gathering where the heat was not. It looked quiet, almost ordinary. But was this really a water machine, or the first clue that the rules of desalination were starting to change? The strange part was not just that the device made fresh water from seawater. People have been doing that for a long time. The strange part was the way it did it. No giant pressure vessels, no roaring pumps, no endless thirst for grid power. Just sunlight, a carefully built surface, a thin film of seawater, and a system that kept pushing salt away instead of letting salt shut the whole thing down. That small scene matters because the need behind it is enormous. In 2022, around 2.2 billion people still did not have safely managed drinking water. More than 2 billion people live in water-stressed countries. Those are numbers so large they can feel numb on the page. But in real life, they mean something simple. A weak tap, a dry well, a long walk, a boiling pot, a child missing school because someone still has to fetch water. Water problems rarely arrive all at once. They creep in. First, a dry season lasts a little longer. Then a river runs low at the wrong time. Groundwater gets pulled up faster than the rain can put it back. A city grows, a factory expands, farms plant more. One hot summer follows another. Soon every pipe and canal that once felt big enough starts to feel too small. That is why water shortages are never just about thirst. They pull on everything around them. Food gets more expensive. Disease spreads faster where clean water is not close at hand. Families spend time carrying water instead of earning money. Hospitals struggle. Schools struggle. Whole towns can look normal from a distance while living under a quiet form of stress that never really leaves. China understands that stress very well. The country has major rivers, giant reservoirs, and some of the biggest water projects on Earth, but it also has a deep mismatch between where water is and where water is needed most. The south is wetter, the north is drier. Many of the biggest industrial zones and major cities sit under tighter water pressure than the national average. Coastal China shows the problem clearly. The sea is right there, vast and blue and impossible to ignore, while nearby cities, farms, and factories still worry about fresh water. Nearly 90% of China's coastal cities have faced some degree of water scarcity. In places like Qingdao and Tianjin, per person water availability has been reported at only 12% and 7% of the national average. That is not a small gap. That is a structural one. So the obvious answer has always been sitting in plain sight. Use the sea, pull salt out, make fresh water. In simple terms, that is desalination. You take water that is too salty to drink or use for most farming, and you remove the salt. The dream sounds perfect. Oceans are huge. Coastlines are long. If the sea can be turned into drinking water cheaply enough, then many shortages start to look less permanent. But the old way of doing this came with old pain. Most big desalination plants use reverse osmosis. That term sounds hard, but the basic idea is easy. Imagine pushing salty water through a wall so fine that water gets through and most salt gets left behind. It works, but the push takes force, a lot of force. And force means energy. Energy means cost. Cost means limits. That is one reason desalination has often worked best in rich places that can spend big money on power, pipes, and maintenance. In Chinese studies, desalination plants were found to use around 4 kilowatt hours of electricity for each cubic meter of fresh water produced. Wastewater reuse can need less than 1 kilowatt hour for the same amount. So even before you talk about steel, land, labor, and repair, the energy bill starts shaping the whole story. Then comes the waste stream. When a plant pulls fresh water out of seawater, the leftover liquid gets even saltier. That leftover is called brine. Think of boiling soup until the water is gone and the salty part is all that remains, only now it is in large wet volumes that have to be handled somehow. If too much brine goes back into the sea near shore, it can hurt local marine life by raising salinity and lowering oxygen. This is why desalination has always carried a strange contradiction. It solves one shortage while creating other burdens. It gives thirsty cities another source of water, but it often demands lots of power and leaves behind a concentrated salty waste. It can rescue a system in drought, but it can also make the water system more expensive, more energy hungry, and more tied to big centralized infrastructure. China still pushed ahead, because in some places the need was simply too great to ignore. Qingdao's desalination plant, built by Abengoa in 2010, was described as producing 100,000 cubic meters of drinking water per day, enough for around 500,000 people. Tianjin built up its own major capacity through projects like Beijiang and Dagang. One Tianjin project reached a planned total capacity of 200,000 cubic meters per day. Those are not experiments. Those are real urban systems. And yet, the old limits never disappeared. Water experts warned that desalination alone could not solve China's water stress, especially if every extra liter kept leaning on large amounts of electricity and large amounts of money. If all of Qingdao's proposed daily desalination capacity had come fully online in the way planners once imagined, greenhouse gas emissions per unit of water would have risen sharply because the power behind the plants still mattered so much. So, when Chinese researchers and engineers began pushing a new kind of solar desalination machine, the excitement was not really about one clever panel. It was about a change in logic. Instead of taking the old system and making it bigger, they were asking a different question. What if the sea could be turned into useful fresh water with much less outside power, and without creating a pool of waste brine that had to be dumped back somewhere else? That is where the machine on that windy test plot enters the story. At first glance, it looked almost too simple. A dark surface, a slant, sunlight, seawater moving in a thin layer. But hidden inside that simple look was a new kind of design. The material had been built to drink in sunlight, hang on to water, and keep salt from crusting over the very area doing the work. Scientists use a term called photothermal for this kind of trick. It only means turning light into heat. You already know the idea from daily life. Leave a black shirt under the summer sun, and it gets hotter than a white one. This machine takes that simple truth and sharpens it. Its dark surface is made to absorb nearly all the sunlight hitting it, instead of letting much of that energy bounce away. In some reports tied to this Chinese breakthrough path, the surface reached solar absorption as high as 90.2%. In another closely related research line led by Chinese scientists, specially treated black metal reached 98% absorbance at peak solar irradiance and around 92% average absorbance across the full solar region. The exact numbers vary by version of the design, but the point stays the same. The surface is built to catch light with unusual greed. That is step 1, catch the sun. Step 2 is just as important. Move seawater across the surface in a very thin film instead of a deep, heavy flow. Think of spilling tea near a paper towel. The liquid climbs through the towel by itself. That effect is called capillary action, which is simply the tendency of liquid to move through tiny spaces. Plants use it, paper towels use it, this machine uses it too. On some of the most advanced versions, microscopic grooves and ridges are cut into the dark metal. Those little channels act like countless tiny roads. Seawater touches the lower part of the panel, then gets pulled uphill across the working surface, even against gravity. Not by a loud pump, not by brute force, by the structure of the surface itself. The water spreads thin, and thin water is easier to heat. That may sound small, but it changes the energy math. Heating a deep bucket of seawater takes more work than heating a very shallow layer. A thin sheet warms quickly. It gives up vapor more easily. The machine is not wasting sunlight on water it does not need to heat. It is focusing the heat where it matters most, at the very place where evaporation happens. Evaporation is the next step. That just means the water changes from liquid into vapor, the same invisible change you see when wet pavement dries after rain. Once the vapor is separated from the salt, it can be condensed back into clean liquid water. That is the basic magic of distillation. Only here, the heat comes from the sun, and the surface has been designed to do more than just get hot. Because this is where older solar desalination ideas usually hit a wall. When water evaporates, salt does not disappear with it. Salt stays behind. Over time, the working area can get coated in crust. The surface that was supposed to make water gets choked by the very salt it is removing. It is like trying to cook on a stove while someone slowly buries the burner under chalk. Real seawater makes this even worse. Lab tests can be misleading when they use simple salt mixes. The ocean is not just water and table salt. It also holds magnesium, calcium, and many other dissolved minerals. Those minerals can form hard, dense scale when water leaves them behind. Scale is that stubborn crust you see inside kettles and pipes, only now it forms inside a water machine where even a little blockage can break the process. So the real breakthrough was not just heating water with sunlight. Many teams around the world can do that. The breakthrough was finding a way to make the salt move away from the active area while the machine kept running. In other words, instead of letting the mess pile up at the center, the device pushes that mess outward to a passive area where it can be collected. One of the clever ideas behind this is something you have probably seen without thinking about it. Spill coffee on a table and let it dry. A dark ring often forms at the edge. That is called the coffee ring effect. As the liquid evaporates, particles travel outward and settle around the border. Chinese researchers used a similar idea to guide salt away from the hottest working region of the panel. Now picture the whole machine like a tiny self-cleaning beach. Seawater enters from below, sunlight warms the dark surface, water leaves as vapor, salt begins to concentrate, but instead of hardening right where the action is, it is nudged outward by the flow pattern and the surface design. Crystals build up on the side, not the center. The machine keeps making water while pushing its own waste out of the way. On some of the best studied versions of this system, scientists described a process called salt creeping. The name sounds odd, but the image is easy. Once crystals begin forming at the edge, a thin film of water moves along them. dissolves a little salt at the inner side, then lets that salt reform farther out, so the crystals slowly crawl outward. The working area stays cleaner than it would in a normal design. That is a big deal. It means the machine is not forced to stop and wait for constant manual cleaning. In one advanced study, the system operated continuously for weeks without maintenance using real ocean water from the Pacific, Atlantic, and Indian Oceans. In outdoor work, one version produced about 10.33 liters of fresh water per square meter per day and around 0.38 kilograms of salt per square meter per day. Those are not fantasy numbers. Another report on a Chinese outdoor prototype said the structure cut the energy needed to evaporate the same volume of seawater by 45.7%. That number is worth sitting with for a second. A nearly half cut in required evaporation energy means the machine is not just a cleaner novelty. It is attacking the most painful part of desalination, the part that has kept the technology expensive and power-hungry for decades. The same report said the prototype showed year-long stability with zero utility energy cost. Read that slowly. Year-long. Stability. Zero utility energy cost. For a water machine, that phrase matters almost more than any single performance number. It means the system did not depend on a steady stream of paid electricity from the grid just to stay alive. That opens doors giant plants cannot easily open. And those doors are not abstract. At a small trial site, the device was used to help irrigate 5 square meters of farmland through a full growth cycle, using only natural sunlight and no external power grid. 5 square meters is not a giant farm. It is roughly the size of a small room. But it is proof that the device was not just making pretty lab data. It was supporting growth in the real world over time. That matters because new water systems usually fail in the jump from lab to life. A benchtop device can look brilliant under perfect light, perfect water, and perfect cleaning. Outside, everything gets worse. Wind changes, dust lands, temperatures swing, salt behaves badly. Operators make mistakes, parts age. If a system can hold steady outdoors for months and support a full crop cycle, even on a small area, people start to listen differently. For a second, imagine your own coastline if you live near one, or the nearest shore you have ever seen. Now imagine that instead of thinking of the sea as a wall between lands, you start thinking of it as a raw water field that can be gently harvested in thousands of small points, not all at once. Not by one giant plant, just one quiet panel at a time. Hold that image for a moment, because that shift in scale may be the real story here. For decades, desalination has mostly belonged to very big things, big pipes, big energy budgets, big contracts, big centralized planning. But this new Chinese direction hints at something else. Distributed water, modular water machines that can sit close to farms, islands, fishery zones, industrial parks, and disaster-hit coasts without waiting for a major grid connection to justify their existence. That does not mean giant plants disappear. They will still matter in major cities, but it means the old choice between huge desalination and no desalination may be fading. There could be a middle layer, not household gadgets, not giant urban megaplants, something in between. Systems large enough to matter, small enough to place where the water is needed, and simple enough to work with sunlight doing much of the heavy lifting. China is especially suited to test that middle layer because it already builds at many scales. It can push giant infrastructure and local pilots at the same time. It has long coastlines, pressured coastal cities, strong manufacturing depth, and a government and industrial system used to scaling equipment quickly once a design proves itself. That does not guarantee success, but it does mean a promising water device in China has a bigger runway than in many places. There is also a reason this story fits China's broader engineering style. China's biggest breakthroughs often do not come from inventing a need that nobody saw. They come from taking a problem everybody understands and pushing hard on cost, scale, deployment speed, and system integration. The country did that with solar panels, it did that with batteries, it did that with high-speed rail. Water may be next. If a solar desalination surface can be made cheaply enough, repaired simply enough, and installed in repeatable units, then the breakthrough stops being one scientific headline and starts becoming an industrial question. Can factories stamp it out at volume? Can coastal towns maintain it? Can farms trust it? Can salt collection be handled cleanly? Can different modules be linked together in rows and still keep their efficiency outdoors? Those are practical questions. But practical questions are where revolutions either live or die. And China has experienced turning practical questions into scale. Look at the path of photovoltaics. For years, solar power was treated as expensive and limited. Then, factories scaled, costs dropped, supply chains tightened, installation exploded. Soon, the old doubts started sounding dated. Water may not move as fast as solar electricity, but the pattern is familiar. There's another fascinating edge to this machine. In some versions of the research, the leftover solid salts are not treated only as waste, they are treated as something to recover. That matters because old desalination systems tend to leave behind a brine problem. A brine-free or zero liquid discharge approach changes that. It means the machine is not making a new liquid mess that must be dumped or heavily managed later. In advanced work connected to this field, researchers even explored recovering useful minerals such as lithium after desalination. Lithium is important for batteries, and mining it from the ground can be energy heavy and environmentally messy. Water machines that make fresh water and also pull out valuable solids are not guaranteed to be gold mines, but the idea is powerful. Waste turns into inventory. A cost becomes part of the business case. That is why this machine should not be seen only as a desert survival device or a village aid tool. It could matter in farming, yes. It could matter in islands, yes. But it could also matter in industrial planning. Coastal factories use huge amounts of water. So do data centers, chemical plants, ports, and processing zones. If some of that demand can be met near the shore without hitting inland freshwater quite so hard, the whole water map shifts. Take islands first. Many islands rely on water shipped in, diesel-driven treatment, or fragile local sources that can go bad quickly in drought. A sunlight-driven desalination system that needs no utility grid could change the daily logic of those places. Not all at once, not enough to do everything, but enough to lower dependence on water tankers, reduce fuel burn, and create a steadier local safety net. Now think about fish farms, greenhouse belts, and coastal agriculture. These are places where water demand is real, but the kind of water needed may vary. Some uses need drinking quality water, some do not. A modular solar desalination setup could be paired with storage tanks and local treatment, giving farmers a buffer right where they work. In water-stressed times, a buffer is often the difference between a saved crop and a lost season. And then there are emergencies. After coastal floods, typhoons, or earthquakes, power lines can fail before thirst does. Pipes can crack, roads can close, central systems can keep running in one district and go dark in another. A transportable or modular desalination system that mainly asks for sunlight and seawater could become part of emergency response in places where the raw water is abundant, but every other support system is damaged. This is also where China's disaster response mindset could blend with its manufacturing strength. A country that can mass produce solar modules, steel structures, pumps, control boxes, and batteries already has many of the building blocks for rapid deployment. If a new water module proves reliable enough, it does not stay a lab object for long. It turns into a product category. Then logistics takes over, then scale begins. Still, this is the point where a careful listener should slow down, because a promising prototype is not the same as a solved crisis. That small black panel on the coast is not about to replace the water needs of Beijing, Tianjin, or Shanghai. It is not going to end drought across inland China. It is not a miracle box that can be dropped anywhere on Earth with no upkeep and no trade-offs. A skeptic would be right to say that. A skeptic would also press harder. They would say 5 square meters of irrigated farmland is tiny. They would say that water systems must prove themselves not for a month or a year, but through heat waves, storms, dirty air, maintenance delays, budget cuts, and human neglect. They would ask what happens when clouds roll in for days. They would ask how much land large arrays would need. They would also ask about materials. Can the surface keep its special properties after years of salt spray and grit? If the device depends on precise laser treatment, can it be manufactured cheaply enough for wide use? If the panels get scratched or fouled, do workers need special training to fix them? Do replacement parts stay affordable? Does performance drop slowly or suddenly? Those are all serious questions. The fair answer is not to wave a hand and call critics negative. The fair answer is to say the critics are doing their job. Water technology should face harder questions than almost any other technology, because failure here hurts people fast. A flashy machine that cannot survive real weather or real maintenance conditions is not a breakthrough. It is a headline. The world has had enough of those. But the critics do not kill the idea, they sharpen it. And when you look at what this Chinese machine has already done, the case remains strong. Strong sunlight capture, lower energy use for evaporation, outdoor stability, no utility energy cost in the test phase. Salt moved away from the active zone instead of shutting the system down. Real field use connected to crop growth. Those are the right kinds of early signs. Just as important, the new machine is solving exactly the part of desalination that has made the old model so hard to spread fairly. It is going after energy dependence and brine waste together. Most water ideas solve one problem and leave the other intact. This one tries to lighten both loads at once. That is rare. And rare in infrastructure is often where the next era begins. There's also a deeper systems point here. China's water future will almost certainly not depend on one source. It will depend on layers. River management, reservoirs, groundwater controls, wastewater reuse, efficiency in farming and industry, maybe more water transfer, maybe better pricing, maybe smarter monitoring. The sea belongs in that mix, but not as a single giant answer, more as a flexible source in a broader portfolio. That is why the machine matters even if it never becomes city dominant. A technology does not need to replace everything to change everything. It only needs to remove key pressure in key places. If coastal industry pulls less from inland fresh water, cities gain room. If coastal farms gain a backup source, drought risk shifts. If islands and rural coasts stop waiting on tanker deliveries, resilience rises. Small edges can reshape the center. History is full of examples like that. Railways did not erase roads. The internet did not erase television overnight. Solar did not erase coal in one stroke. New systems enter at the edges first, where their strengths matter most and their weaknesses hurt least. Then they improve. Then scale changes the argument. That is the pattern this machine may be following right now, almost quietly, while most people are not paying attention. And if that pattern holds, the next step will not be one giant announcement. It will be many boring ones. Pilot expanded. New manufacturing line opened. Coastal agriculture trial extended. Island project approved. Emergency use unit tested. Water cost benchmark updated. Salt recovery improved. Maintenance interval stretched. These are the dull-sounding sentences that usually tell you a breakthrough is becoming real. It is also worth noticing how this machine fits the climate era. Climate change does not only reduce water in some places, it makes water less predictable. Rain arrives in bursts, snowpack shifts, dry seasons drag on. Floods and droughts can hit the same region in the same year. A water system built around one grand source becomes fragile when weather patterns become less stable. Distributed systems gain value in that world. Sunlight has its own limits, of course. Cloudy weeks happen. Monsoon weather happens. Coastal land can be expensive. But solar-driven desalination does not need to work alone. It can pair with tanks, batteries, microgrids, wastewater reuse, and rain capture. The smart future is not one machine replacing all others. It is different tools covering for each other's weak spots. China has become very good at building those layered systems. There's a political meaning to that too. Centralized water systems put power in centralized hands. That is sometimes necessary, but when some water can be made locally from sun and sea, options spread outward. A fishing town gains flexibility. A farm cluster gains flexibility. An island gains flexibility. In a century where resilience may matter almost as much as raw capacity, that spread of options becomes a strategic asset. So what might the next 20 years look like if this machine and others like it keep improving? First, you would likely see more coastal demonstration farms and industrial pilot zones. Then you would see standardized modules designed to be installed like energy equipment rather than bespoke water monuments. After that, if costs keep falling, insurers, port operators, local governments, and farm groups would start treating these units as normal infrastructure. At that point, the conversation would shift from can this work to where should this work first. Small islands would be high on the list. Aquaculture clusters, greenhouse belts, military outposts, tourism zones with seasonal water spikes, chemical parks where freshwater competition is intense. Even wealthy cities might use modular solar desalination not as their main source, but as a peak shaving tool during hot, dry periods when the rest of the system is under strain. And China could become the place where that market gets built. Not because no one else can invent pieces of it, but because China is very good at combining invention, manufacturing, and deployment pressure in one place. That is often what turns an interesting machine into a global product. The world may remember the first dramatic headline, but the world lives with whoever learns how to build 10,000 units reliably. This is why the phrase solve the global water crisis should be handled carefully. No single machine will do that. Not this one, not anyone. Water crises are too tied to money, politics, pipes, pollution, farming, and inequality for a lone device to sweep them away. But a machine can change the cost curve. It can change the deployment map. It can turn one impossible option into a normal one. That is how crises start to loosen. And when that happens, the change often feels slow until it suddenly feels obvious. One year, a panel on a Chinese coast looks experimental. A few years later, you see arrays near greenhouses, then at island ports, then beside industrial parks, then packed into emergency response containers, then copied by other countries. By then, the old question is gone. Nobody asks if sun-driven seawater machines are practical. They ask why they waited so long. Go back now to that March morning in eastern China. The engineers still crouched near the panel. The sea is still cold and restless beyond the test plot. The dark surface is still drinking light. Along the edge, the white salt line keeps inching away from the center instead of smothering it. Drop by drop, a clean trickle forms. Nothing in the scene is loud. That is part of what makes it so striking. Because most megaproject stories begin with concrete, steel, noise, and scale, this one begins with a surface, a texture, a thin film of water moving where it should not be able to move, rising against gravity in tiny channels, giving up its vapor to the sun, leaving its salt to crawl harmlessly aside. It feels less like a factory and more like a lesson from nature that engineers finally learned to copy well enough. Maybe that is the real reason this story feels important. It is not just another tale of China building bigger. It is China, or at least Chinese, led science and engineering, pushing towards something lighter, more distributed, more patient. Less about crushing a problem with force and more about shaping surfaces so the problem starts solving itself. That kind of shift can look modest at first. Then it changes everything built after it. If you like spending time with stories like this, subscribing helps me keep making them. Now I want to hear a real argument on this one. If countries had to choose in the next decade, should they put more money into giant, centralized desalination plants or into thousands of smaller solar machines like the one China is testing along the coast?